Okay, hey, welcome back. This is triple integrals in cylindrical and spherical coordinates. So first cylindrical, and of course cylindrical is basically just polar coordinates plus a z-axis. Okay, so in the xyz plane, we can describe a point in space using firstly an r theta point in the xy plane. Okay, so we can describe that location using the angle theta that it makes with the x-axis, and then some directed distance r, and then you just go up some distance z. Okay, so this point that's sitting right there in space would be r comma theta comma z. The usual conversion formulas apply, so the x is r cosine theta, y is r sine theta. Remind yourself the other, this x squared plus y squared is r squared in case you need that. Z is just plain old z. Okay, so it's not too difficult if you've already mastered the polar coordinate system. When we move to actually figuring out volume, then what you have, instead of having cubes, excuse me, you have cylindrical blocks. Okay, so they're not exactly blocks in that they get bigger as you get away from the origin, right? So anyways, we'll say that little block there, call it delta V sub I, will have volume R dr, delta R, I guess we should go R sub I. R sub I, let me put it in black, delta R sub I, delta theta sub I, delta Z sub I. Okay. Right. So it's not your usual block like you would see in the rectangular coordinate system. And you can see a nice picture of it there in 14.63. I won't try to draw it any better than what I did. Okay. All right. So the triple integral, then you're basically just tacking on an r. You'll typically do z first, okay, and then just z dz dr d theta, okay. So let's kind of just first see if we can actually. The first couple of problems are basically just integral problems. Do you know how to integrate yet? Then problem 4, they start investigating the limits on integrals. So let's look at problem 4. 0 to 2 pi, 0 to 2 root 3, and then r squared minus 4 to 8, and then you have your integrand r dz dr d theta. Okay. All right. So the innermost integral, if you look at the limits on there, you're going to be going from the surface z equals r squared minus 4 to z equals 8. Okay. So that top limit, z equals 8, is just a plane. Right, so that's not a big deal. The bottom limit, what the heck is that? Z equals r squared minus 4. What I would recommend is to rewrite that using your conversion formulas and get it back into rectangular coordinates so you can get a handle on it, right? So z equals r squared. R squared is x squared plus y squared, and then minus your 4. Okay, and then it's a quadric or quartic, whatever the heck they call those things, right? So look at the xy plane. In other words, let z equal 0, and basically x squared plus y squared is 4. So you get a circle in that plane. Look at the yz plane, so you let x equals 0, and you get z is y squared minus 4, which is a parabola shifted down 4 places. And then look in the xz plane, and you get sort of the same thing. Z equals x squared minus 4, which is just another parabola shifted down 4 places. So elliptic paraboloid, and that will be the bottom curve, right? So you have this plane at z equals 8 cutting through space, and then below it you have your elliptic paraboloid kind of going like this, doing us to draw it. And then there would be kind of a trace here if you so desired. But the XYZ axes, let's go ahead and get those kind of drawn. It would look like this. Okay. The pictures are terrible. These are the worst graphics I've seen in my entire life with respect to three-dimensional graphing. I would like to have a talk to the people that wrote this software. I feel for them though, because they probably had to use something that was free, and more and more people are saying, well, how much money do you have? So it's this one right here. It's the only one that looks like a kind of like a parabola. These other ones are just craziness. So definitely that one. And then they just want you to do the integral, which is no big deal. You guys can do integrals. The next one is a spherical. So problem 5 is actually in spherical coordinates. So I kind of need to introduce spherical coordinates. I never use them. I was actually listening to a book while I commute, a flat earther guy. I just like arguing. I'm terrible at arguing, so I figure if I listen to these guys, I'll become better at it. But in the book, he often drops, spherical coordinates and stuff like that. And I think and I hate to say it, I presume he does that because they want to kind of present themselves as somebody that knows what they're doing, and probably there's a large part of the population that doesn't know what spherical coordinates are, right? So if you just say spherical coordinates, a lot of people will drop the argument and not follow any further. So flat earthers get a lot of flack for their beliefs, and I try to understand what the heck they're talking about. So personally, I'm not an astronomer. I don't go outside in my yard and look up at the sky. Probably if you asked me to, I wouldn't be able to prove that the Earth is round. I don't remember how to do that. They taught me when I took astronomy, but I don't really remember. So anyways, push comes to shove, I feel like if I get in an argument with a flat earther, I'd probably lose. But anyways, it's a good idea to deal with spherical coordinates. It's the coordinate of choice. Actually, I think there's a lot of different coordinate systems if you're dealing with astronomy. There's several, but I could be wrong about that. I just don't know enough, So you got to be careful. I don't want to run around saying I'm a flat earther or anything, being abducted into their kind of, I don't want to call it a cult. I don't want to be insulting, but you know what I mean, anyways, you should know something about spherical coordinate systems. So the way this works is kind of, again, you're describing points in space. So you have a point right here in space. To get to that point, what you're kind of doing is dropping down from the z-axis. Okay, so you have a z-axis, and you're coming down by some value phi, and then the distance of this line here, the directed distance on there, is kind of like an r value, but they'll call it rho. Okay, so the distance of that, this line here that I just drew in red, is rho. In the xy plane, it's basically the polar coordinate system that they use to describe it. So there's a theta involved right down here, and then you could still this would be a right triangle, although it's not drawn very well. You could still describe everything kind of in terms of polar coordinates. So you could describe this other length down here in the xy plane with r, but you're not going to see the r in the spherical coordinate systems. Okay. Anyways, what we want to do is generate another set of conversion formulas for spherical, and you can kind of pull that off using ideas from geometry. So first, note we have some alternating interior angles here. This angle is going to end up being phi as well, right? So if you extend this, you'll have like a transversal going through, alternating interior angles, so therefore that's equal to phi. And from there, you could say that the cosine of phi And because this distance right here is z, the cosine of phi is going to be equal to adjacent all over hypotenuse. So that would be z all over rho. So you get a nice little formula for z. So z in this case is not just z. You're going to be able to convert it to rhos and phis. So it's going to be rho cosine phi. Okay. And then I need formulas for x and r. So for x, you can start by trying to just use the polar conversion formula, so r cosine theta. Then what you're going to do is get a formula for r, right? So what is r? R is basically, you can get it from the sine of phi, right? So it's the sine of phi, I guess. So sine of that blue phi here, opposite, which is r, all over hypotenuse, which is rho. Okay, so we could say that r is equal to rho sine phi, and then plop that expression into this expression, and you have a nice little conversion formula for x in terms of rhos and phis and thetas. So rho sine phi cosine theta, and then y, by the same kind of explanation, will be rho sine phi sine theta. Okay, so we have those conversion formulas. The object that you have, the three-dimensional object, is a bit different, and the way we get to it, because of all these weird rotations that we're dealing with, let's see if the book gives you a nice little picture again so I don't have to draw it. Yeah, it's right here. Okay, so it's kind of tilted. The spherical block this time it's tilted in this direction, and it has kind of an odd shape to it. But anyways, let's get the volume increment. So delta v sub I is going to be, weirdly enough, rho sub I squared times sine of phi times delta phi sub I times delta rho sub I, delta phi sub I, delta theta sub I. Okay. All right. So right. So hopefully that'll be enough to kind of get you through. Note, instead of r, like r dz dr d theta, you have this factor here. And when we talk about Jacobians, it'll become more clear what that thing is. It's basically kind of like the result of a chain rule, so to speak, when you're dealing with substitution, a multivariable substitution on an integral. Okay. Anyways, what you're probably not used to then is actually graphing in spherical coordinates. This is why I kind of avoided it in the homework. It's really good for plotting spheres and cones. In particular, there's extra conversion formulas, which I'm not seeing here, which we probably introduced when we originally talked about spherical coordinates. It seems like back in the day we had a previous section on it. Let me see if it's in the book somewhere. Integrals. Where the heck would that have been? It would have been in double integrals, right? Change of variables. Did they do it there? This is the first time we've seen spherical coordinates. Yeah, so this is the first time. Usually they give you a bunch of conversion formulas. That's what I'm kind of looking for. So I'm surprised. It's, for some reason, I don't know why, I think we even have it in spherical. Yeah, so for spherical, I guess we're not going to get the conversion formulas. It doesn't really matter anyways, because I'm not giving you homework in that regards. But yeah, usually you'll have a set of conversion formulas that you can use, and it's kind of like the r squared, x squared plus y squared equals r squared, that kind of stuff. You basically have x squared plus y squared plus z squared equals rho squared. So in particular for problem 5, let's look at the setup. Okay, so I have the integral from 0 to 2 pi, integral from 0 to pi, integral from 2 to 5, rho squared sine of phi, d rho, d phi, d theta. Okay, so the first innermost limit is rho. Rho equals 2 to rho equals 5. Okay, so going back to the picture, what the heck is rho? Well, if you look here, there's a right triangle, right? Okay, there's a right triangle sitting right here. So we should be able to kind of construct a formula for rho. Rho would equal, in this case, r squared plus c squared. Rho squared is r squared plus c squared. So if you replace r squared with x and y squared, rho squared is x squared plus y squared plus c squared. Okay, so you can kind of generate similar formulas in that way. And then down here, you have rho equals 2 to rho equals 5. Well, we can rewrite that. So when rho is 5, we have rho squared is equal to x squared plus y squared plus z squared. In other words, 25 is equal to x squared plus y squared plus z squared. And what the heck is that thing? That's just a sphere, right? It's a sphere with radius 5. And then, of course, rho equals 2 is just a sphere with radius 4. So surface to surface, what we're doing is kind of going from a sphere of radius 2 to a sphere of radius 5. So you should have some sort of, looking at from the side, just the cross section and the xz or yz plane, you should see something like that, right? So pretend we're in the xz plane. Looking over at your choices, you kind of have to, this one looks like it could be correct, but it's not, because the outer sphere is too big, and then this sphere looks like it's good enough. Okay, and their pictures are so bad, sometimes you have to guess, and then you have to be able to integrate. Great. Anyways, the rest of the problems, and there aren't a lot, are just converting to cylindrical coordinates, or setting up an integral in cylindrical coordinates. So let's go ahead and just take a look at those and get those off our plates. Some of these kind of are challenging. All right, so anyways, use cylindrical coordinates to find the volume of the solid. We have a sphere and then the top part of a cone, right? So looking at it in the x z plane or the yz plane, the object will look like this. Okay, so clearly you know that first thing is a sphere, the x squared plus y squared plus z squared equals 16. You could do your trace analysis if you don't believe me. The other guy, maybe it's not as clear what the heck this thing is. But you can always, again, you just do that trace analysis like we taught you. I'm going to square both sides. The only problem with squaring both sides is now the sort of domain becomes bigger, right? Originally, z has to be greater than or equal to 0. So you just sort of remember this factoid as you go to figure out what the graph is. So z equals x squared plus y squared. What is that? And you do your trace analysis in the xy plane. You'll have x squared plus y squared equals 0. And that's just a point, right? If you push out from that, so if you let z equal 1, for instance, you get a circle. Okay, so what's happening then in the xy plane, right here you have a point, and then if you go in the z direction, and z has to be greater than or equal to 0, so you can't go downwards, you're going to get these concentric circles. Okay, and you could already see it's basically just a cone. All right, but anyways, going to the yz plane, then you get like z squared equals y squared, and of course that would be just two lines going back and forth. So yeah, it's going to be a cone. I mean, z squared equals x squared plus y squared is a double-headed cone, like it would go down, but because z is greater than 0, we just have this cone in the xyz plane, and then when you look at the cross section, it's basically a triangle. Okay, so I need to find what the solid inside the sphere and outside the cone. So it's basically this region that we're looking for the volume of. It's kind of a sphere with the top like a notch taken out of the top. Okay. All right. So in the XY plane, I'm going to be integrating over a circle. So the way I approach this, I think I had to think about it for a little bit. What I did was find the volume of a sphere and then subtract away the upper volume, this wedgy volume. I thought that was easier. So the volume of a sphere, which you should know, it'll become helpful later on, 4/3 pi r cubed. So in this case, I know that the radius of this sphere is 4. So my volume of the entire sphere is going to be 4 cubed times 4. I'll just write 4 to the 4th all over 3 pi. Okay. And then I'm going to find that volume of that blue region. And in order to pull that off, it's basically, surface to surface. So, and we have to think in polar terms eventually here. So it's going to be r dz, dr d theta. And I'm going to be going from z equals the lower portion to z equals this upper portion here. Okay, this upper surface. So the lower surface is the cone, and the upper surface is the sphere. And to put it into polar coordinates, you just use your simple conversion formula: x squared plus y squared equals r squared. Okay. So the lower curve is sitting right here. So converting that into terms of r's or whatever, r's and thetas, z would be the square root of r squared. In other words, z is just equal to r. R is always assumed to be positive. So I'm going from the cone, and in cylindrical coordinates, that's just r. Z equals r. And then I go to the sphere. Okay, and because I only need the upper hemisphere, I can solve this equation for z. Right, so I have z eventually equals the square root of 16 minus x squared minus y squared. And again, I use the conversion formula to rewrite it. Z equals the square root of 16 minus x squared plus y squared. And then you can replace the x squared plus y squared with r squared. Right? So then that becomes your upper limit, square root of 16 minus r squared. And then for the inner integrals, you're thinking of what region am I integrating over? And basically that's just the projection of that cone object into the xy plane. You're going to be a little careful because you might try to think it's all the way out to here, but it's not. It's right here, and it's hitting here. So you'll basically have this region that you're integrating over, right? Anyways, and that would be in the, I guess the y axis would be like right here, and I'm going to have to integrate out to that. Right, so it's not the radius of that circle that I'm integrating over is not equal to 4. Right, you got to be a little careful. So what exactly then is that point? Well, you could take the intersection of the cone and the circle, and then letting z equal 0, figure out where that is. So let's take our formulas here and here and kind of put those together. So I'd have x squared plus y squared plus putting in z for z squared, x squared plus y squared equals 16. So it would be 2x squared plus 2y squared equals 16. I kind of just need the radius. So divide everything by 2 and I get 8. So the radius is square root 8 of that circle. So r equals what to r equals what? So in the xy plane you have a circle with radius r. I just need basically the polar coordinates, or the polar equation for that graph. So r would equal the square root of 8 basically, or 2 root 2. So I'm going from 0 to 2 root 2, I believe. And it must be 2 root 2. I don't show it on my... And then on the outermost integral, I'm going from 0 to 2 pi. Okay. Let me just dump that into Wolfram to make sure it's right. And please do the integrals on your own. You need practice doing integrals. Don't just go the Wolfram. Anyways, I just want to make sure it's set up right. I don't have the integral written out or anything. Instead of r, I'll just use x. Hopefully that doesn't upset anyone. Equals, or rather, z equals x square root of 16 minus x squared. Parentheses, comma. The next guy is x equals 0 to 2 square root of 2. Let's put a multiplication symbol in there because the computer is an idiot. I got too many parentheses there. And parentheses, comma. Then finally I'll put y, I guess on the outside, equals 0 to 2 pi. Okay, push enter and hope I get the same thing I got when I did it earlier. Let's see. And of course I get some weird answer. Yeah, it's close to being the same thing. Okay, Cat, thank you. What the heck did I do wrong? Did I put it in right? Okay, let me pause the video for a sec, see what I did. Oh, I forgot, I still have to subtract. So the answer, is kind of that, but it's really this, I forgot this portion. I have to subtract that thing away from that. All right, so you have to go this minus that, and then that'll give you the answer. I forgot, I only found the volume of that blue region. Okay, so you have to subtract the actual sphere volume, first the sphere and then subtract away. Okay, and then you should get the answer that the software is giving you. Should I dare? I feel like if I put that in front, it's just going to have a fit, 4 to the 4th times pi divided by 3 minus this thing. I bet it won't do it. Dude, I don't understand what it means. Yeah, see, it's getting all upset about it. So let's hit that again. Wolfram alpha. So 4 to the 4th star pi over 3 minus this thing, which is negative 64, so it become plus 64 thirds times square root of 2 minus 2 parentheses star pi, and of course I put 2 minuses in there. That doesn't look right at all. Minus 64 thirds square root 2 minus 2. They got a nice form for it somewhere? No, they're not going to help me out. 4 to the 4th pi over 3. Oops, maybe if I got rid of that, it would be a little happier. Okay, there it is. There's the answer there, and the alternative forms. Did I trash my... No, it's still there. 14.7. There it is. Okay, so finally we got it. Yeah, kind of annoying. It's a weird object that they had you to figure out there. Number 7, kind of the same thing, except you don't have to do the additional part where you do the subtraction. Number 8, let's try that one then. And make this one the video quiz, and then we'll be done with it. Let me mark that in my notes. So this is video quiz set number 8. This will be the third problem in that set, 14.7. This is problem 8 in WebAssign. Okay, got it. So anyways, the solid bounded by the sphere, r squared plus c squared equals 25, and the cylinder r equals 5 cosine theta. So r equals 5 cosine theta, first off, in the xy plane, what the heck is that? That's going to be a circle. It starts out at 5 and then dies to 0, and then it goes negative, increases back to 5. One issue, this is really traced out from 0 to pi, so you want to be careful about that. And then if z is allowed to vary, because this is x, this is y, it'll go up into your space, right? So it's going to, if I put like a z-axis here, it's just going to then go in this direction. Okay, so it'll be a cylinder. Of course, reorienting it then in the XYZ place, you know, what is it doing? It's on the x-axis, kind of popping out like this. We have a sphere we're kind of dealing with, right? So a sphere with radius 5, that will kind of go like this, and this. Okay. And the cylinder will kind of be like a tube through the sphere. Okay, so it's gonna, let's see if I can draw it. Let's see if that may be asking too much at this point, I'm afraid. So anyways, it's going up and up and up, and eventually it'll go through the top of our nice sphere. And also this sphere goes downwards too, so you know it's going to go through the top and the bottom of the sphere. So eventually it'll rear its ugly head going through this sphere like this, and then you'll have kind of a top of it. It's kind of like a contact lens looking thing, and then we have the, you know, the bottom going all the way through the bottom part. Okay, so at the end of the day, if you extract this object and then extend it downwards, it'll kind of look like this. Okay, where there's kind of a rounded top and bottom because of the sphere, the roundness of the sphere, right? So what I'm going to do first off is cut that sphere in half, okay, and just figure out basically the volume of this top part that I kind of already have built over here. Okay. All right, so that formula then, that being said, so originally it was r squared plus z squared equals 25. Now I can rewrite it as z equals 25 minus r squared, square root of. And of course I'm going from basically the xy plane up to that, up to the sphere over top of that region. So the region I'm integrating over is the r equals cosine of theta. So this region here is what I'm integrating over. So going from, in my integral, in the innermost integral, I'll go from z equals, I guess the r cosine theta, the cosine theta part, I lost my 5 somewhere. There should be 5 cosine theta. So 5 cosine theta, I'm going to have to multiply the whole thing by 2 because I cut the volume in half. So 5 cosine theta 2 all the way up to the sphere, which is square root of 25 minus r squared. Okay. And then I have, of course, our r dz, dr d theta, and then moving out on the integral, surface to surface, right? So actually the bottom surface is just z equals 0, and then I can restrict the region using this xy plane formula, the r equals cosine 5 cosine theta. Sorry about that. So it's going from r equals 0 to r equals 5 cosine theta, and then of course 0 to pi. Okay, so that would be our integral. I'm just going to go to Wolfram and use the computer to figure it out at this point. So let's go to the computer. I think I have like 20 tabs open. Okay, so I already have one set up for triple integrals. I need to put just basically x in there. And I'm making this x, and I'm making this my y. Okay, so I'm going from 0 to square root of 25 minus x squared, and then 0 to 5 cosine of y, and then y equals 0 to pi. And at the end, I need to multiply it by 2. It's not happy about it. Must have forgot a parentheses. Yeah, it's not happy about it. Exceeded the computational time. I may have to just do it by hand, do it the old-fashioned way. So it's 2 times, might as well do one integral. This is a video quiz still. So we get rz dr d theta. This will be 2 integral. I have to evaluate this for z. So it's r times the square root of 25 minus r squared dr d theta. I'm going to have to do a u sub on that portion. Negative 25 minus r squared. So du is negative 2r dr. So dr is negative du over 2r. So this, you can factor out a negative 1/2. It's a negative of the double integral of the r's will cancel, and then you just have u to the positive 1/2 du d theta. And then power rule to integrate the u. Back subbing, I get 25 minus r squared to the now 3/2 times 2/3. I'll pull out the 2/3. And then I need to evaluate that thing from 0 to 5 cosine theta d theta. And then I got negative 2/3 integral of 25 minus 25 cosine of theta squared to the 3/2, and then minus just 25 to the 3/2. And then I could simplify the heck out of this guy, right? So that's really just 25 sine squared theta. That raised to the 3/2 power is going to be 125 sine cubed theta. So I'm getting negative 2/3 integral of 125 sine cube theta minus 25 to the 3/2 is 125 d theta. And then you factor out the 125 times 2 is, I believe, 250 over 3. And then you have the integral of sine cubed, which you can rewrite as sine theta times sine squared theta. Sine squared theta is 1 minus cosine squared theta. Then minus 1 d theta. Then you'd have to do a u sub on the first portion of your integral. So you get negative 250 thirds integral, whatever the heck that thing is, minus this other integral, which will become just 1 d theta. Sort of. There's that pesky negative 250 over 3, so it'd be plus 250 over 3. Then doing a u sub here on cosine. du would be negative sine theta d theta, and plugging that in, this sign right here is going to cancel. This will become u, and then there's a negative floating around. So instead of it'll become u squared. Instead of 1 minus u squared, it'll become u squared minus 1. So you get u squared minus 1 du, and then that will be negative 250 all over 3 times power rule on it, u cubed over 3 minus u. I have to evaluate that eventually, plus 250 thirds theta. Evaluate that thing as well. So I get negative 250 cubed, back subbing cosine cubed theta all over 3 minus cosine of theta, evaluated from 0 to pi, and then plus 250 all over 3 theta evaluated from 0 to pi. So this will be negative 250 all over 3. Cosine of pi is negative 1. Negative 1 cubed is negative 1 over 3. Minus cosine of pi is negative 1. Minus, plug in 0, you get 1/3 minus, I guess just 1. And then plus 250 thirds pi. And then, simplifying a little bit, this junk will become 2, it's like 2 minus 2/3, right? So that'll equal 1/3. And so you get 2 minus 2/3 is 6/3, sorry. 2 minus, this will be 6/3, so that'll be 4/3 rather. So negative 250 thirds times 4/3 plus 250 all over 3 pi, and then that'll be negative 1000 over 9 plus 250 over 3 pi. Okay, so that'll be your video quiz. Alrighty then, that should get you through the homework if nothing else. And as usual, thank you for watching, and sorry if I offended any flat earthers. I get it, you know, it's like most people really couldn't convince me that the earth is round, but I think ultimately the earth is actually round. So that's just my opinion, you know. It's a well established opinion over hundreds of years. I think it's just hard because, you know, people have to take so much for granted at this point, because you can't exactly go back and relearn, you know, 1,000 years of material on astronomy. You know, nobody is going to have that kind of knowledge in their brain, so you have to take a lot of it just on assumption, just because somebody else told you it was true. And I mean, when you're dealing with reality and facts, you kind of want to know that the person that told you all that stuff isn't lying. And I guess the astronomical community can be very, very, you know, closed off to other people in society. If you don't have like a telescope, I mean, how far can you really get with regards to astronomy, you know? So it's kind of an elite class of people. It's a very small community. It's kind of hard to make money doing that stuff. So they become the caretakers of knowledge, and if you're not part of that, you kind of feel like you're on the outside and you're just taking everybody's opinion almost. So I get it. I get it. I don't think flat earthers are stupid or anything like that. It's not that. I get it. So, anyways, there's all that kind of. I'm talking about it because the spherical coordinates is used for, sometimes used for orbits, I think. Okay, but like I said, there's all kinds of coordinate systems out there. Go look up, coordinate systems for outer space, and you'll see there's more than one. Systems for satellites. You have like orbital coordinate systems. I don't even go to. Okay, so you see there's these weird. I don't even know what they are. It gets pretty technical really fast. So anyways, there's that. Thank you for watching. I'll see you next time.